Can I start? It's okay. Okay, so let's start the session. Okay, so hello everyone. Welcome to the AsiaGraphics webinar session 7. So I am the chairperson for this session. So I'm Yuki Koyama from ICE and Graphinica, Japan. And today we have two great speakers. So the first speaker is Professor Weiwei Su from Zhejiang University, China. And the second speaker is Minhyuk Son from KAIST, South Korea. And each speaker will have 45 minutes, including discussion time. And just as a reminder, we welcome any questions or comments. So please don't hesitate to post your comments to the chat box. Okay. So now I'd like to introduce the first speaker. So the first speaker is Weiwei Su. So he is currently a full professor at State K Lab of CAD and CG in Zhejiang University. And he was a researcher in Internet Graphics Group at Microsoft Research Asia from 2005 to 2012, and a postdoc researcher at Ritsumeikan University in Japan. And he received his PhD degree in computer graphics from Zhejiang University and bachelor and master degrees in computer science from Hohai University. His main research interests include 3D reconstruction and image-based rendering and virtual reality, and has published more than 90 papers, including 30 papers on ACM transactions of graphics, science robotics, CVPR, ICCV, triple AI, and IEEE TVCG. And he received Outstanding Researcher Award from NSFC in 2013. And today he will talk about a neural indoor scene rendering with reflections. So Professor Su, please start your talk.
Okay, thanks a lot for Yuki's introduction. So I will share my screen. So is everything okay?
Currently, I can see that. Yes.
Okay.
Yes, that's perfect.
Okay. Thanks again for the introduction. And my topic today is neural scene modeling and rendering. Let me first introduce some background. So as we all know, the rendering is the core research direction in computer graphics. Given 3D geometry, materials, and lighting, so we can solve the rendering equation to obtain realistic images. So thus, the rendering technique can be viewed as a forward inference engine. So after we change the geometry, materials, or change the light source in its position or something else, so we can use the rendering engine to render the new image, so we can infer how the geometry change influence the image change. So however, the forward rendering process has some technical challenges. So since it is expensive to compute, since it needs recursive computation to render global animations, and this also very expensive to design good high quality 3D contents. Finally, it's had to be used in inverse modeling. That means we cannot use directly with the captured images. So recently, the development of neural rendering techniques try to approximate the forward imaging process using network. So actually, in computer vision, the neural rendering is classified all the techniques that can generate images is classified into neural rendering. But in this talk, we'll talk about the how to use the neural rendering techniques to approximate the forward imaging process. So here's an example. So given the neural network, so we can input the viewpoint, geometry, lighting into the neural network. Then after some computations inside the network, we can output an image. So it's called a neural rendering. So with after we use a neural network to approximate the rendering process, we can compute the derivatives. We can use backward propagation to compute derivatives to from the neural network to viewpoint, geometry, and lighting. So it's the advantage of neural rendering. So there are several questions need to be solved in neural rendering. So how do we represent input using explicit way or implicit way? Second is how to design network and how to integrate the rendering knowledge that already have been developed in computer graphics in neural rendering. So the term neural rendering actually starts from a science paper from DeepMind in 2018. So, so this is the network they designed in this paper. So given some observed images, they can learn some latent representation of the neural scene. Then we can train a rendering network to render the scene at a different viewpoint. So after we give the network a few images of the scene, the network can learn how to render the scene in varying viewpoints. So
没事，反正我们现在这一块是主要是还是为他们自己渲染好这块 OK。
So although the input image is quite simple, is from the computer rendered images, but its potential has been verified. So after the science paper, there are a lot of research works on the neural rendering.
哎，我就先宏观上。
So here's another paper from Scene Representation Network from NIPS 2019. So it tried to develop a neural network to learn a function. So given viewpoints, 3D positions, they can render image. So this is the network. So this paper first, may be the first to use MRP network to predict the color of a 3D point along in the rematching. So this is the network structure. So given the viewpoint, so the rotation, the translation, and this a projection matrix. So we can unproject rays for each pixel on the image. So we can use this network, use the MRP network to compute, to obtain a feature and then convert it into a color. So this is so this paper can model much more complex things than the science paper. So this is some results. So it can also generate novel views even given only a single view. So that means the network has already remembered some knowledge how to predict the novel view of an object. So this is the famous neural reading field paper. So it adopts spectral positional encoding to improve the quality of the rendered image. So given the ray and the viewpoint, the neural reading field network can approximate the rendering process very realistically. So it can be viewed as the network can remember the light field. So it's the view interpolation result. So it can also simulate the view dependent effects. So in addition, the network can generate high quality depths given multi-view input images. So it can be directly used in some augmented reality applications. But the neural reading field can only handle static object, so without light change. So in the outdoor scene of for example, from internet images, the user might take the image at a different time in the day, so the lighting will change. So it's very difficult for neural radiance field to directly handle such kind of input. So this is neural radiance. This is extension of the neural radiance field network. So it's called neural radiance field in nerve in the wild. So it can learn some appearance embedding latent code to handle the change of the light. So we can see some results here. So it's the input. So it's unconstrained photo connection. So the light will change in different photos. So after they learn some appearance embedding latent vector, they can use this vector to handle different kinds of images to obtain realistic rendering result. So you can also change the lighting using the appearance embedding vector, using that vector to control the appearance of the rendered image. Here's some cool results. So furthermore, if we import lighting, we can also import lighting as a latent representation into network to handle the change of the light. So this is another AsiaGraph paper. So they use the synthesized data as the training data. Okay, so they can handle the light change. So they can simulate the time-lapse effects for natural scenes. Okay, so they also use internet images to test their network. So this is the constructed geometry, and after the training, they can simulate the light change. So next, I will introduce our work on neural rendering. So this is our paper on last year's AsiaGraph, scalable image-based endorsing rendering with reflections. So the background is for indoor scenes, we can frequently observe some high-frequency reflections, high-frequency of beauty-band reflections in the scene. So such as specular reflection, glossy reflection, or mirrors. Although there already exists some image-based endorsing rendering research works like inside-out deep blending or free viewpoint synthesis, and some developed devices to capture view-dependent effect. They cannot efficiently render high-frequency reflections in larger scale indoor scenes. So this is a comparison between our work and the state-of-the-art deep blending network. So we can see that our algorithm can produce temporally coherent reflection results with realistic reflections. We can observe the reflections on the table. So there are two technical contributions of our work. First one is we develop a global mesh guided robust two-layer mesh construction algorithm. So given the captured image, we actually build two-layer mesh representation for the image. So the first layer is the surface layer mesh. It represents the diffuse component of the image without specular or high-frequency reflections. The second layer is a reflection layer mesh. It represents the environment geometry reflected by the table and the reflect colors, reflect highlights. The second one is the temporally coherent image-based rendering. So first we develop a view selection method that can take the previous frame into consideration. And then we also develop a neural network to render the final result. We call it a super resolution network, since we downsample the texture image, since we want to save the memory footprint of the image based endorsing algorithm. So we can see the super resolution network can rectify the artifacts after image warping. So this is the magnified view. We can see that the random results can be significantly improved. And since we use super resolution network, our IBR pipeline, image-based learning pipeline, can support densely sampled images due to the saved text storage. So we can support more than 2,000 photographs for an endorsing. But originally, the previous work only used several hundred images, even though less images can save the capturing efforts, but it is very hard for them to capture the high frequency reflections. So this is our pipeline. So the first pipeline is geometry processing. We first do some per view geometry processing and construct two-layer mesh. And the second, after the two-layer mesh construction, we develop a rendering pipeline. It consists of view warping. It's like the traditional image-based rendering. We do view warping with steps, and then we use a rendering network to output the final rendering result. So let me describe our pipeline very quickly. So first is global mesh reconstruction. So we use multi-view reconstruction and collective fusion to reconstruct geometry. So this is the multi-view reconstruction result. And there are some holes in the textureless area, so we can use collective fusion to improve the quality of the reconstruct geometry. So this is the reconstructed geometry for endorsing. The second step is we want to refine the depths at each view. So the purpose of this refinement is to align the geometry image with the image, geometry edge with the image edge. So that way to reduce the tearing or ghosting effects in the view blending. So we can see some mismatch between the geometry edge and the image edge. So we can do refinement. So this one, we first remove the misalignment between the geometry image and the mesh and the image edge. So then we do the edge-aware depth interpolation to align the geometry and the image edge. So with the refined geometry, we construct the surface layer mesh. So the last step in geometry processing is the two-layer representation reconstruction. So for each captured image, we want to decompose the image into surface and the reflection layer images. That means we use a linear composition assumption to obtain the separation. So the image IK can be decomposed into IK0 is the diffuse image and IK1 is the reflection image. So the beta is a mask to indicate where the reflection is in the image. So it's the reflection mask. So actually the reflection mask indicates the reflective surface in the image. So and it's the surface layer image and the reflection layer image. So we can see only the reflected things are remained in the reflection layer image. So actually to robustly obtain the reflection decomposition, we use the global mesh, reconstruct global mesh as a prior information to enforce some constraints. So the first one is we want to detect some reflective planes in the scene from the reconstruct geometry. So this is used another SQL paper algorithm. So we can use a cost volume to detect whether there are multiple peaks in the cost volume for reflective plane detection. Then we do some reflection mask detections. So after we obtain the reflection mask, we can use the an optimization algorithm to obtain the two-layer meshes and the two-layer images. So this is the objective function. The optimizing variable in our algorithm is the rigid transformation of the reflection layer mesh, and the geometry of the non-rigid transformation. This is the like the displacement vectors for the surface and the reflection layer meshes. So finally, we want to obtain the surface and the reflection layer images. So for the to initialize our optimizing variables, we use the global geometry as we mentioned before. So we use the surface layer mesh to initialize the M1, MK0, and we use the reflected mesh, the reflected global geometry mesh. The reflection is along the reflector plane to obtain the reflected geometry. The surface, the reflection layer mesh, so it's MK1. Okay, so with these two layer meshes, we can walk the image between the different views to obtain the initialization of IQ0 and IQ1. Okay, so it's the multi-view warping. So we use the mean composition to obtain the initialized IQ0. So it means the initialized surface image, diffuse image, and we directly subtract the diffuse image from the original image to obtain the initialize the reflection image IQ1. Okay, so the optimizing objective function actually consists some data term. So it's used to constrain the rendered image to be similar to the original captured image. Okay, this is the visualization of the data term. So we also use some regularization term or prior term to regularize the optimization. So the final one is the multi-view consistency check. So since we are capturing multi-views of a scene, so we can use the multi-view images to constrain constrain our solution. So we can, so the details can please refer to our paper for details. Okay, so here we show some decomposition comparisons. So given the reference image, so we can use some deep learning based or some geometry based reflection separation and reflection decomposition algorithms. So this one is from the SIGGRAPH of 2012. So we can see without the explicitly reconstruct geometry, their decomposition result is not good. So the second one is from a deep learning based reflection decomposition algorithm, but we can see they cannot reconstruct the reflection well. So this is our result. So since we already reconstructed global geometry, so we can obtain much more robust reflection decomposition results. So this video shows the rendering result with and without decomposition. So we can see here. So without the reflection decomposition, we can see blurred rendering results on the TV screen, and the reflected ground. So with two-layer mesh reconstruction, we can see realistic rendering of the reflections. So we can see the reflections on the white board. So for the rendering pipeline, we first do some rewalking. This is very similar to the traditional image-based rendering technique. But we develop a novel view selection scheme. So this is the view selection. So, but we want to take the previous frame into account to remove the temporal jittering. So this is a visualization. So, but we intentionally separate separate the space surrounding the current virtual viewpoint into different regions. So we can, and we use already, we also put the already selected views in the previous frame in these regions, so that we can reduce the sudden change of the selected viewpoints for the view blending to improve the temporal coherence. So, and we also do some floating geometry removal before we do image blending. This we use a image-based rendering course to reduce the influence of the floating geometry. So after this, we can do some blending. For blending, we also take care of the depth boundaries. So we use some width decay along the depth boundaries, so we can reduce some tearing or ghosting effects. So after rewarping, we already obtained some initial rendering result, but it contains a lot of artifacts. So we develop a neural network to refine the rewarping result and obtain the final images. So this network is adapted from the supersampling network in SIGGRAPH 2020. So in the supersampling network in SIGGRAPH 2020, so they assume the rendering result is from a game. So the geometry is perfect. So that means we can obtain very clean depth data. But in our case, since we reconstruct the geometry from multiple images, there are many noise inside in our preview refined geometries, preview refined depths. So we add a motion rectification module inside the network to reduce the error caused by the inaccurate depths. So this is our motion rectification module. So we can see the effect of the motion rectification module. So without the motion rectification module, we can see many errors. So the white color indicates larger errors between warped frame and the current frame. So after motion rectification, we can reduce such kind of errors. So this is the effect of the motion rectification module. So we can see the boundaries can be improved. So with the supersampling network, we can reduce artifacts in the view warping result. So, for example, the ghosting at the image boundaries. So this is the aliasing at the edge of the table. But after the network, the artifacts can be removed. Here we show a demo comparison between view warping and the result after super resolution network. So in this slide, we show some statistics of our reconstructed indoor scenes. So the areas of the indoor scenes and the capture number of images and the storage required for each scene. So we can see, and we also compare our algorithm with some state-of-art image-based rendering algorithms for indoor scenes. So we can see our result is on the top left, so we can realistically render the reflections in the mirror or the highlights on the sofa. So we also compare our results with NERF. So we can see the NERF results can generate not bad results, but there are still some artifacts there. So here we show some quantitative comparisons. So for this kind of, for the things we reconstructed in our paper, we can obtain very good PSNR and the SSM scores. So we are almost achieved the best PSNR and SSM scores. So here we show more results. So this is a hotel room. So we can see the reflections on the frame of the this picture. So we choose notch translation motions of the virtual viewpoint. So here's the field case of our algorithm. So our algorithm mainly handle the planar reflective surface. So it might produce some blurred render result for curved surface. So this is the ground truth, but our render result is blurred. So in future, we want to research on how to exploit rendering knowledge to improve the generation ability of neural rendering. And we want to investigate how to use the neural rendering work to improve the reconstruction and rendering result simultaneously. So this may be also a very hot research topic in neural rendering. So so in the following, I will introduce our network on reflection removal, so called location-aware single image reflection removal. So it's published last year at CCV. So in the previous work, we used multiple images to render the indoor scenes with reflections, but in a lot of situations, we might take photos behind the glass. So there may be very strong reflections on the glass. So we want to remove such kind of reflections. So as we know, so the strength of the reflection is determined by the Fresnel term in optics. And after the spectral refraction, the light will be polarized. So we can use a polarizer to remove the reflections, but it needs some hardware, so we cannot use it in our, maybe like for example, mobile phone or our cameras. So there are a lot of research work on how to remove the reflections in single image using optimization or neural networks. So since there are many number of unknowns, so for each image pixel, we need to determine its reflection color and its transmission color. So it's an air-posed problem. So not priors such as gradient sparsity, relative smoothness, or Gaussian cues have already been introduced in single image-based reflection removal. However, they all assume that the reflections are not strong or somewhat blurred at the boundary. Therefore, for some strong reflections, that means their boundaries is very sharp in captured images. This method usually cannot obtain good reflection removal results. So, for example, we choose some reflection removal results with state-of-art deep learning-based reflection removal algorithms. So this is the ERNet, so IBCLN, so IMNet, and they are all state-of-art deep learning-based reflection removal algorithms, but we can see the reflections are still remained on in the result. So So here is our network, the result of our network. So we propose a location-aware single image reflection move network. So that means we use we train network to learn a reflection confidence map. So that means we train the network to learn where is the stronger reflections to detect the reflection dominant regions and then remove the stronger reflections. So this is our result. So the stronger reflections on the original image, captured image, is almost removed. So it's comparing with the state-of-art deep learning-based reflection removal algorithms, we can see the difference. So this is their result. So this is our result. So this is the additional results. So we can see we show that our network can detect the reflections, strong reflections from the input image. So our observation is that we can use the Laplacian operator, a second differential operator, to suppress the low frequency reflections, and then we can use the difference between the original image and the image processed with the Laplacian operator to detect the stronger reflections. So here we show 2 examples. So this is the original image. So if we use the first order differential operator like to detect like edge operator to detect edges, we can see the reflections still remains in the edge map. However, if we use the Laplacian operator, we can see that the low frequency reflections, so that means the reflections is blurred in the captured image. We are hardly to see the blurred reflections after the image processed by the Laplacian operator. So that means we can use the difference between the original image and the image processed by Laplacian operator to suppress the low frequency reflection, since there are no and then detect the stronger reflections. So here is the stronger reflection detection results. So we use multi-scale Laplacian features to detect the reflection area. So we call it the reflection confidence map. That means we detect some stronger reflections. So you can see the white area indicates there are stronger reflections. So it's the predicted reflection layer, and it's the recovered transmission layer. So we use the original Laplacian operator as the initialization, and we network to learn the weights of the Laplacian kernel. So our network actually is iterative network like IBCLN. So we developed a reflection detection module. So this is the architecture of the reflection detection module. So we use the multi-scale Laplacian operator to obtain the multi-scale Laplacian features. Then we input the features into residue block to get the features, and then we predict the RC map. And the RC map is trained in an unsupervised way, so it can be clarified in our learning loss after introducing learning loss. So this is the autoencoder to recover the transmission layer. So we use the convolution plus ReLU plus a lightweight attention-based module called CBM to reconstruct a transmission. So this is the result. So the training loss. So we, since we don't have the ground truth reflection map for each for each image. So we use an unsupervised way to train the network. So that means the network only needs to be trained by the MSE loss between the predicted image and the ground truth transmission image. And we use this. We use a linear blending formula, like in this one, I equals W multiplied T plus R. So W is the mask, T is the transmission, R is the reflection. So we directly use this this formula to train the network to predict the reflection confidence map in an unsupervised way. Okay, so here is some of the quantitative results. So it's also we also use the PSN and the SSM metric to measure the quality of the predicted transmission image. So this is our network can produce very good transmission images. So it's ranked as number 1 or number 2 in all the tested data sets. So here we show some qualitative results. So this is the comparison between our reflection results with 4 existing state-of-art deep learning-based reflection removal methods. So this is the original image, mixed image. This is the results of other methods. This is our result. So we can see our result can remove more reflections on the image. That means that it doesn't mean that it's perfect. There are still some remaining reflections, but our results is better than other methods in these qualitative comparisons. This is another comparison. So our method can remove the reflected highlights. Okay. That's all for my talk today. So thank you for watching.
Thank you very much for a great talk. Okay, so now we are in the Q&A session. So let me see if we have any questions or comments from the audience. So yeah, the audiences can ask questions by using the chat box at the live streaming service. So I think there is no question yet. So, okay, so let me ask a question first. So about the first method, so in my understanding, the method is for specifically designed for indoor scenes. But yes, I'm wondering what is the primary difference between indoor scenes and outdoor scenes? Or in other words, I'm wondering whether this method, the proposed method, can work with outdoor scenes such as buildings with reflective glasses or something like that.
Okay, so we apply this method to indoor scenes for 2 reasons. First one is that we mainly handle reflect planes. So for indoor scenes, there are many planes, right? So it can handle. So our method can handle such kind of reflections. So the second one is we use global mesh to construct a 2-layer representation. So for auto scenes, if the auto scene, if a reflected surface is reflecting the sky, so there may be no global mesh there. So so it's a limitation of our network, but we can use the neural rendering technique to handle such kind of things. So anyway, I think the principle of our work can be applied to outdoor scenes, but it may be some specific adaptation of our algorithm. I think it's not very difficult.
Thank you. Thank you very much. So
you're welcome. Okay.
any questions from the audience? Maybe not yet. Okay, so then let me ask another question. So about the second method, so this is a quick question. So what happens if the target object itself has strong highlights?
Okay, so that means there are strong highlights in the transmission, right?
Yeah.
So my answer is that we depends on the difference, not the. So in our pipelines we use the original image. First we compute the Laplacian feature of the original image, and then the Laplacian features of the transmission images. So it actually depends on difference. So in the original image, if we use the Laplacian operator, the low frequency refraction is already suppressed. So in that area, the difference might be very small between the original image and the predict transmission images. So that's the reason why we can detect stronger reflections. So if the object in the transmission image contains the strong highlights, but the difference is still minor between the image processed by the Laplacian operator. So that means we should be able to handle such kind of highlights in the on the transmission, the highlights on the transmission objects, since we are based on difference, not the Laplacian operator. We're based on difference after the Laplacian operator. Maybe it's a little bit involved.
Yeah, thank you. Thank you for the answer. So in my understanding, there is no questions from the audience, and it's time to move on to the next speaker. Okay, so thank you for the talk. Great talk. Thank you.
Thank you, Yuki. So,
yeah.
Okay, so I stop screen sharing. Okay.
Yeah. Okay, so let's move on to the next speaker. Okay, so I'm sharing my screen. Okay, so the second speaker is Dr. Minhyuk-san. So Minhyuk is an assistant professor in the School of Computing at KAIST. And before joining KAIST, he was a research scientist at Adobe Research. And he received his PhD from Stanford University under the supervision of Professor Leonidas Gibas. And his research interests lie in vision, graphics, and machine learning, with a focus on 3D geometric data processing. And his work was featured at SIGGRAPH Asia 2017 for a press release. And today he will give a talk titled Discovering the Compositional Structure in 3D Shapes from Supervised to Unsupervised Learning. Okay, so Minhyuk, please share your screen and start your talk.
Okay, great. Can everyone see my slide and hear my voice?
Yes.
Okay, thank you. Yeah, thank you for the great introduction. So today I'm going to talk about discovering the composition structures in the 3D shapes. So I'd like to start my talk with some high-level ideas. So we know that many objects we are seeing the daily lives have these structures that decompose the object into the multiple parts. So basically, the objects can be decomposed with some semantic labels with the names that people call the parts, and also with the parts that have some different ways of interacting with the people. Basically, the functionality, some parts can be some areas where the people grabs with the hands, or the other parts can be or the places where the people sit. So where the parts of the objects can be also defined based on some kind of the some appearance informations like some materials or the textures that are assigned to the parts, whereas based on the mobility, basically how the parts are articulated and the moving. And the idea of like understanding this kind of the entire the object from the composition structure, basically its parts and their arrangement in the space, is a kind of the old idea that has been investigated for a long time from back in the 1970s. Basically, the 1970s was the time when the pioneers of the computer vision and the cognitive science, like Thomas Binford and the David Moore, basically first they conceptualized the idea of like recognition by the components, basically perceiving a object by seeing it as kind of the arrangement to be some simple geometric components. And this idea has been evolved for a long time in the history of the computer vision and the machine perception to better basically perceive the objects. And using the composition structure in the 3D modeling and also the editing is also very common in the computer graphics and the CAD applications. And most of the CAD and the 3D modeling tools are basically designed in a way that the user can basically place like some small and the basic components in the space and they composite them with some kind of the operations like the CSG operations here to create the final completed shapes. So when basically dealing with some kind of scan data, also solving the reverse engineering problem, basically recovering this kind of some structural information from the raw geometry is also very important problem to enable some many applications like the shape editing and the manipulations. And also in the robotics, learning such kind of the compositional structure is a kind of the essential task. So for the autonomous agents, it is not sufficient to just kind of recognize the object, but the agents need to know like how to interact with objects, like which parts you should press to open the, for example, open the door or like they pour the water from the bottle, and what is the place in a cup to pour the water, basically. So these are basically some information about the parts of the objects, and we need to know how these parts are basically arranged in a object. So, and to learn this kind of this structure, the information, basically the 3D data would be basically the best type of the data, since basically it matches the physical form of the actual objects. We can basically describe the objects as it presents in the real space. So unlikely with the images, basically when you deal with the 3D data, you don't need to worry about basically the viewpoints or the occlusion or some variations coming from the different lightings. So you can, for example, like this directly discover some kind of the part structure by for example fitting some bounding boxes or detecting some primitives or discovering some symmetries or some repeating patterns or finding some common components across the different shapes in the same category. So along the direction of the learning some compositional structures in the 3D shapes, recently there has been lots of the work, especially based on the neural networks. So PointNet is one of the base architecture processing the 3D data, which can also segment the input shape, input point cloud into the multiple semantic parts. And especially the segmentation has been more actively investigated in the case of like handling some scene data. And people will solve both the semantic segmentation and the instance segmentations based on the scene data like the TT data set or the ScanNet the benchmark. And more recent work basically focused on the learning this kind of the part structure even without having any supervision, but by just fitting some sort of the some primitive shapes like the bounding boxes or the super quadrics or more complicated some kind of convex shapes. And also such effort was not limited to some human-made objects or the scenes, but also extended to some non-rigid some kind of the deformed shapes like the human bodies and the animals. So in my talk, I'm going to introduce some my recent works all about the learning the composition structures in the 3D. So one is about the primitive fitting, and I'm going to explain why the supervised learning is basically needed in this kind of problem, and what would be the kind of the best way that we can leverage some supervisions in the primitive fitting. And the second one is about the unsupervised method that can learn the decomposition of the parts using the deformations. And the last one is basically about the weakly supervised method that can learn the semantic parts from the shapes, but without any ground truth the semantic segmentations, but from some language descriptions of the entire shapes. So let me start with my first work, which is the supervised learning for the primitive fitting. And here, let me first briefly introduce the exact problem that I'm going to solve. So here the problem is that given a 3D shape, which is represented as a point cloud, so we are finding a set of the geometric primitives that can best describe the input shape. So as here, and also we consider 4 types of the primitives, which are the planes, cylinders, and spheres, and the cones. So let me turn on the razor here. Sorry. Okay, cool. So yeah, so and the output should basically include the number of the primitives and also the types of the primitives and also the parameters of the primitives and also the supporting areas in the input point cloud to each of the primitives. Basically, why we solve this problem? So this is, very fundamental problems in the computer graphics, and also these days, the 3D scanning and the CAD industries are very much interested in this problem. So this is basically, the reverse engineering problem, basically converting the scans into the CAD. But obviously, a CAD file can contain some more, complicated information that just kind of having the primitives, but this can be still kind of the first step of like converting the scans to the CAD. So here, what I'm going to say is that despite the big advance in this 3D scanning the technology, the lack of this kind of some converting tools like converting the scans into the CAD basically became a kind of the bottleneck to extend the applications of this scanning the technology, since the raw point cloud cannot be used in many applications like the shape editing and the manipulations. So the scanning industry has dealt with this problem actually by providing a kind of the manual service. So basically they hire some kind of the expert, the CAD designers, and they let them create a 3D model that can exactly match the scanned shapes. And basically these are the names of the companies that provide this kind of the service. And as you can imagine, basically it takes huge amount of the time and also huge amount of the cost that because everything is basically manually done. So basically we want to have a kind of the fully automatic the pipeline that can do this kind of the scan to CAD conversion. And such kind of the reverse engineering is also needed not only for the scan data, but also for some kind of 3D models in the online repositories, since most of these 3D models that we can see in the online the databases are basically typically represented as kind of the meshes, basically the vertices and the faces, and the original the CAD information is basically missing. So this kind of like recovering the CAD information is also very important to exploit the 3D models in the many in the online repositories. So basically, if you see this problem, this is basically is kind of just primitive fitting problem that you can just apply any kind of some typical estimation techniques like the rank set and the half transform. And also actually the technique that is known as kind of the state of the art for this primitive fitting problem before actually our method is also the rank set based method, which is called the efficient rank set. And this efficient rank set is actually kind of nothing but just kind of iterating the rank set multiple times for each of the primitive type. So you randomly sample some of the points over the input point cloud and define a primitive. And if it has the sufficient number of the inlier points, then you take the primitive and also take out the inlier points. And you just repeat this process until there is no remaining points. So this, and also this algorithm is also implemented in the CGAL, which is the famous geometric processing library. So you can try this algorithm yourself. And here the point is that actually this is a kind of the estimation problem that we can actually solve without the neural net. So let me quickly remind the difference between the prediction problem and the estimation problem. So for the prediction problem, like classification or detection or the recognition, basically, in the test time, we cannot measure the correctness or the quality of the outputs. So basically, to measure the quality or the correctness of the outputs, we need some kind of the extra information, which is typically not given in the test time, but only in the training time. So this the extra information in the training time is basically the supervision. So we train the neural net to memorize this kind of the patterns of the what is the good answers for the inputs. And based on the kind of the inductive bias that the neural net learns, the neural net can basically predict the good answers without the measuring the quality of the outputs in the test time. So these are the big problems that we typically solve with the neural net. But in the estimation of the problem, basically there is a way that we can measure the goodness of the output in the test time. So without the basically any kind of a learning process, you can basically solve a optimization problem and find the best model that optimizes the evaluation function. So in the primitive fitting case, the evaluation function can be the distance from the primitives to the input point clouds. So basically the distances from all the primitives to the point cloud are very small, then we can say that the output primitives basically rarely construct the input shape. So this is basically a problem that does not require any kind of the supervised learning. Then why we talk about the supervised the learning in this case? So here the issue is that the estimation, the problem that we are solving is basically ill-posed, meaning that when you find the solution based on the criteria, basically the distance from the primitives to the points, the best solution with respect to this criteria may not be the solution that we want to see. So here the example is that we have a shape of the board which has the top, the part which has the 6 side planes here. But depending on some small random noise added to the input point cloud, actually the best solution, minimizing the fitting error from the primitives to the point clouds, can be the case of like splitting the single plane even into some multiple small primitives, or it can be the case like grouping the multiple side surfaces into the one cylinder. So these are basically all the possible cases, like minimizing the distances from the primitives to the points, depending on the noise, which are basically presenting in the input point cloud. But here, actually the solution that we want to see is like having exactly the 6 side planes here. So this means that the reconstruction error, the distance from all the primitives to the points, may not be the best measure to capture the sort of the people's expectation, like having the 6 side planes in this case. And if we also use the rank-based method, the only way that we can handle this kind of sensitivity to the noise with the method would be basically to fine-tune some the rank the algorithm parameters, such as the fitting errors, the fitting error the threshold, or the crossing the threshold. But this kind of like tuning or like the tuning the parameters requires lots of the human inputs, so it becomes like impossible to make any kind of the fully automatic pipeline. So here we propose an idea of like leveraging some supervision to better solve this problem. And this is the work that we published in the CDPR 2019. And before we go into some details of like how to leverage this supervision, let me first explain how we acquire this kind of information. So in our setup, basically the supervision comes from a large-scale 3D CAD model data set. So the basic idea is that we basically synthesize the 3D scans by sampling points over 3D models and also adding some random noise. So we also show that our network trained with this kind of synthetic data can also work well with the real scan data. But here, basically, the benefits of like using this kind of the synthetic point clouds they created from these 3D CAD models is that we can basically take the full supervisions from the 3D CAD models. So we can have not only the ground truth information about the primitive parameters, but even more we can actually have some even more information about the shapes. So we are going to develop a neural network that can fully exploit all these informations coming from the CAD models. And going back to the algorithm, so here the key question is basically how are we going to design a neural network for this kind of supervised learning? So for that, one option would be still train the neural net with the same reconstruction laws, basically the distances from the primitives to the input point clouds, as same as like running the rank-based pipeline. But then, there's nothing different with the rank case. So basically, we're going to see the same ill-posedness problems that basically the neural net falls into the local minimum. And the other option would be basically predicting the parameters of the rank set in the rank-based pipeline. And this is also not easy problem because the iterative process, like taking some primitives and removing some inlier points, these are basically non-differentiable the process. So for training the neural net, we actually might need to use the RL-based the approaches to solve the problem. And the other option actually would be directly regressing the primitive parameters. But this is also not easy problem because neural net is not good at basically solving this kind of the regression problems, basically predicting some absolute informations. So here, our key idea is that instead of like directly somehow predicting some primitive parameters, we predict some intermediate attributes using our neural network and then map this information to the final primitive parameters with the kind of the differentiable function. So for example, so here this is basically the naive case when we have the input point cloud X and also the neural network F, which is basically actually predicting some the primitive models, the primitive parameters. So this is the naive case, and we are going to change this formulation like this. So here the G is the new neural network, which is not predicting the primitive parameters, but some sort of the intermediate attributes. And now this kind of the output, the attributes are mapped to the final primitive parameters using the given and the fixed function H. So this H is not learned, but this is kind of the given differentiable function. So here the idea is that basically we are finding the best primitive parameters from this kind of intermediate outputs, this gx, by solving a kind of the optimization the problem. And actually this function h is basically the analytic solutions for the optimization the problems. And the good thing of like having this kind of change of the formulation is that now we can have some kind of the extra the loss functions for the intermediate outputs, the gx here, based on the supervision that we can get from the CAD models. And these new loss functions actually play the critical role of making this formulation to be well posed and also improving the quality of the outputs. So if I show the diagram of the architecture, so this is the naive case that we are directly regressing the primitive parameters. Now we want to switch this architecture like this. So here the output of the neural network is this intermediate the attributes here. And this is fed to the function h here, which is not learnable function, but this is given and the basically fixed and also differentiable function. And this function actually outputs the final the primitive models, but the primitive parameters y here. And since this given function h is differentiable, the good thing is that we can also run the backpropagation from the end to end of the pipeline in the training. So I also show in the experiments that how much this kind of the end-to-end training is important in the performance. So now let me go into a little bit more details about the neural net architecture. So there are 4 main parts. So at the very beginning, we take the input point cloud and then process this point cloud using the backbone architecture. So here we basically use the PointNet++, but any architectures processing the point clouds can be used here. And this part basically returns 3 types of the per point attributes. And basically these the attributes are the intermediate attributes that I called in the previous slide. And these 3 the per point, the attributes are basically the labels for the primitive, the segmentation, and the labels for the primitive, the types, and also the point normal information. So basically the first 2 are basically solving the problems of the instance segmentation and the semantic segmentation. And so from these 2, we can basically decompose the input shape into the parts and also decide the types of the primitives. And the last one is basically the first derivative information of the geometry, which is especially useful to estimate the axis of the cylinders and the cones. So once we have this kind of the per point information, the intermediate attributes, in the next step, now we compute the primitive parameters that best fit the each of the segmented parts. And here, since now we know how the input shape is exactly segmented into the parts and also know the types of the primitives for each of these segments, and given the types of the primitives, we can solve the optimization of the problems for the fitting. And now we can also even derive analytic solutions that minimize the fitting error from the points to the primitive surfaces. So we are basically, the idea is that we are basically figuring out this sort of the segmentation problem at the first part, so that we can make the problem easier in the rest of the pipeline. And the analytic solutions becomes the differentiable function h here, which is mapping the intermediate attributes to the final the primitive parameters. And so this is the basic idea. And I'm not going into some details in the formulation, but you can check out some details of like how we derive this kind of the analytic solutions in our paper. And once we compute the primitive parameters, now we need to compute the fitting losses and also other losses. But for that, actually, the thing is that there is no basically the fixed order of the primitives. So the order of the ground truth primitives that we have in our the training data can be different with the order of the output primitives. So we don't have any information like which primitive should be the first and which primitive should be the second and so on. So since we don't have this kind of the order information, what we need to do is that we need to match the ground truth primitives with the predicted primitives. So for that, what we do is that we basically reorder the output primitives by computing the fitting errors for all the pairs of the ground truth primitives and the output primitives and find the best one-to-one correspondences. And for these pairs of the ground truth and the output primitives, now we compute the loss functions. So for the loss functions, we have the fitting loss, obviously. And as I mentioned before, now we have some supervised losses for the 3 types of the intermediate attributes. And this supervision basically comes from the CAD models that are basically used to synthesize the input point clouds. So we basically have the 3 more loss functions, which are the segmentation loss and also the type classification loss and also the normal loss. And additionally, we also use some extra one more supervision, which is basically the axis of the some of the primitives, like for the cylinders and the cones. We also have some extra loss functions for the angle of the axis. So when you train this network, we can get this kind of the output. So these are some examples of the results. And this is also a comparison between the results of the our framework on the right-hand side and also the result of the rank set-based method. And this is one of the actually very challenging case that we have some two very close cylinders, which are the inside and the outside of this kind of thin part of the shapes. And these two surfaces can be very easily confused in the rank set-based pipeline, but our framework can precisely distinguish these two surfaces. And this is another challenging case that we have some two cylinders, which also the radii are almost the same. So the rank set-based method cannot see that there are actually two cylinders here, but our framework can easily segment these two. And this is another case that we have some multiple small cylinders inside this kind of the big green plane. So this is one of the also the challenging case that we have some very different scales of the primitives. Like one is very big and the other one is very small. But also even in this case, our network can successfully find all the small primitives and also the big primitives. And this is also the quantitative comparison showing how many points in the input point cloud are basically explained by the alpha primitives when we basically vary the threshold for the distance. So in this graph, basically higher is better. So compared to the case of like the rank set-based method, the rank set-based method is the blue line. And also the case that we are directly regressing the parameters using the network, which is the red line. So compared to these blue lines and the red lines, you can see that the method like combines some predictions of the neural net and also the optimization gives some way better results with some very huge gap in this graph. And despite also the domain gap between the training the data that we are using, which is basically the synthetic point clouds and also the real scans, we also found that our network actually works well even with the real scan data. So here are some of the examples that we are basically finding some very tiny and the very thin primitives from some real scan data of this kind of the mechanical parts. So here basically we show that how a supervised learning can be leveraged to solve a kind of the estimation, the problem, basically fitting the primitives to a point cloud to improve the performance. And we also show that the 3D CAD models can be used to provide some kind of the extra to the supervision, which is actually especially very useful in this case to make the problem much easier. So this was the first part. Do we have any questions for this first part? Now let me move on to the second part. So yeah, now let me move on to the second part. So in the second part, actually, I'd like to talk about some deformations. So actually, the composition of the structure that we are discussing now is actually also very important to make some variations of the shapes. For example, here, when you know that this airplane is decomposed into the two wings and the one fuselage here, then we can try to, for example, like translating like the wings like this and also elongate the fuselage. But if we don't have such kind of some semantic the part information, then sometimes it's not easy to create some kind of the some realistic and some plausible some deformations. So without the part structure, actually we can still try to make some deformations with some deformation handles. There are lots of the techniques like using some control points like here or some kind of the cage message here to make some deformations. But the limitation of such kind of work in the perspective or like making some user interactive some tools is that it does not guarantee that the output of the deformations basically makes sense. So for example, what I'm going to say here is that when we have some kind of the key points of the chair like this, we know that like the bending the leg toward the left or the right, like here, we're just pulling down like one leg while keeping all the other legs is kind of like breaking the chair. So we are not making the chair as kind of a chair. So the chair with this kind of information won't look like a kind of the another chair. So to make some kind of the plausible deformation, basically they make the chair like the chair, we need to know like some kind of semantic or some structural information about the shapes. So here, our goal is to basically learn some kind of the intuitive or some kind of the some user-friendly some deformation handles that are also aligned with some kind of semantic meanings and also produce some kind of the plausible deformations. So we also propose to learn this kind of some intuitive handles without any supervisions about any kind of the semantics or the structures, but by just kind of learning from a large collection of these 3D shapes in the same category. So let me first show some examples like the output of our neural network. So each of the columns on the right-hand side here is the outputs of our networks. So our network basically predicts some kind of the intuitive handles that deform each of the parts in the shapes. And as you can see, like, basically the first one is kind of like repeating the C part, and the second one is kind of like raising the armrest, and the third one is kind of like the tilting the back part, and the first one is kind of like changing the width of the chair, so and so on. So there are kind of many other kind of the handles here. And our learned is kind of the deformation handles are also kind of the consistent across all the shapes. So based on that, a user can also edit a collection of these shapes simultaneously. So let me also show our demo basically editing the 3D shapes. You can actually also play with this demo in the link, which is encoded in this QR code here. So you can basically see that there are multiple some deformation parameters that are learned by our the neural network on the right-hand side here. And every time when the user basically moves these kind of sliders, you can see how each part of the shapes are basically changing here. And these changes are also very consistent across all the chairs, despite the kind of the different structures of these kind of the shapes. And here also, the most interesting part is that we do not use any kind of information about this kind of the parts, and also there are kind of the semantic deformations in the neural net training. But the neural net is basically self-supervised in a way to learn about like what would be kind of some natural way of like factorizing the deformations into some interpretable some deformation handles from the given collection of the data. So here we see how basically the neural net learns the underlying some part structures of each of the shapes and how to decompose the shape into these some multiple parts. And this is our work, which is published in the CVPR last year. And let me explain the high-level idea of this work. So as the input, basically we take a 3D shape and also some geometric deformation of the deformation handles. So as the input handles, we use some random control points that are automatically created using some farthest point sampling algorithm. And using the bounded bari-harmonic coordinates, we basically can define a deformation function from each of the key points, the FC here, that basically describes how the entire shape should be changed when we move each of the key points here. And the deformation function defined with key points is basically the linear. So we can represent this deformation function as kind of the matrix, the W here. And our goal here is to produce a set of the new deformation handles based on the given deformation handles. And these new handles are basically defined as a kind of the linear combinations of the given deformation functions, given the deformation functions which are defined with the contact points. So this is why we call the new handles as kind of the math handles. So the neural net basically outputs the linear combination weights of the given contact points for each of the math handles. And actually, we can interpret this as kind of like predicting some basis vectors in the space of the given the control point parameters. So, for example, here we have the C number of the control points, and then basically this means that we get the C times 3 number of the parameters because every point can have the three-dimensional coordinates. So in this space, we are basically predicting m number of the basis vectors, which become our learned method handles. So basically, we want to find a set of the basis vectors in the given parameter space, so that each basis vector becomes aligned with some kind of semantic part and their deformations. And we also enforce these basis vectors to be independent of each other, and still also make them to span a kind of the linear subspace in the given the parameter space that can only include some kind of the plausible deformations. So this is basically the basic setup. Again, the inputs are basically the input shapes, and also the randomly sample the control points over the input shapes, and also the deformation function defined with the given control points, which are basically the biharmonic coordinates. And our network first predicts the set of the linear combination weights, basically that define each of the meta handles here. And also here, the thing is that actually you can think this as kind of the setup of the conditional generative models. So once we have the set of the meta handles and also produce some kind of the random deformations based on the meta handles, we can actually add a kind of the discriminator that tests whether the deformation created by the meta handles are basically looks like the real or the fake. So precisely, we're predicting not only the set of the basis vectors, but actually we predict a kind of the distributions over the given the control point, the parameter space, so that when you sample randomly sample any points over the distribution, then these parameters can create kind of the realistic shapes through the deformations. So if we consider this as kind of the conditional the GAN model, so here the condition is basically this input shape. But here the difference with the typical conditioned GAN model is that in our case, the generator is not learned, but actually this generator is given. Basically, in our case, this generator is kind of the deformation, the functions defined with the given the control points. So what we do is that we actually not learning the generator, but given the fixed generator, actually we are learning the distributions of the plausible shapes over the given the deformation, the parameter space. So this is kind of the one difference with the typical generative models. And the other difference with the other conditional general model is that, in the typical conditional GAN, the thing is that the domains of the input and the output data are basically different. So we can consider some models like converting black and white images into the color images, or some daytime images into the nighttime images, or converting a sketch into the some real images. And these are basically all the cases that when the input itself cannot be a kind of any kind of the desired outputs. So basically, you need to make any changes in the input to make a kind of the realistic outputs. So when you convert the sketches into some real images, the sketch itself cannot be a kind of some real images, but you need to make some kind of the changes into the input to make a kind of the real images. But the problem in our case is that the input and the outputs are in the same domain. So which means that both the input and the outputs are the 3D shapes in the same category. So if you do not make any deformations, any change into the input, then this input itself actually becomes the perfectly plausible shapes, the perfectly plausible the output data. So if you use a typical conditional GAN setup in our problem, here the problem is that the neural net does not learn any deformations because the input itself is the perfect the outputs. So the learned distribution in our case also actually becomes a kind of the sort of the Dirac delta functions, which peaks is at the zero deformations. So what we do here is that we basically add another module called the deform lab here, which basically randomly picks a target shape in our database and tries to match this kind of target shape by making some deformations based on the learned math handles. So basically, in order to match the random target shape, the learned distributions over the control point of the parameter space should not be a kind of the sort of the Dirac delta function, but it should be kind of expanded to cover all the random target shapes. So basically, this enforces that the learned distribution to include all the possible deformations. And as the loss functions, we use the multiple loss functions, both for the geometry and the disentanglement. So I'm going to skip some details here, but here we use a kind of the regularization loss that disentangles the statistically independent some deformation factors into the multiple math handles. And this actual loss function plays the important role of like discovering some symmetric parts and their plausible deformations. So let me skip some animations here. And as I mentioned, we also have a website where you can play with this kind of demo yourself. So please check this out. So here I introduce like how we can create a conditional subjective models that can learn some kind of the plausible deformations and also deformation handles that can produce some plausible the outputs, like some changes of the shapes without having any supervisions about the parts and their structures. And also I briefly mentioned that how the symmetric part, the structures can emerge from the learning the independent factors of the deformations. So I'm already running out of time, so let me go quickly with the last part of the presentation. So actually the last part is also about the 3D segmentation, but based on the language description. So we know that the 3D annotation is actually quite challenging and also time consuming. So while the data annotation itself is very time consuming task, actually it is especially very challenging in the 3D case because it requires also some kind of skills like playing with some kind of a 3D interface. And also the annotation is not done by just making some few mouse clicks, but actually you need to change the viewpoint and annotate the shapes from the multiple directions. So these challenges in the 3D annotations might be actually one of the reasons that why we don't see many of the large-scale data sets for these 3D shapes with the annotations. For example, MS COCO data set, the data set for the images basically include more than 300,000 images with annotations, but for the PartNet, which is the more recent data set, including 3D models, actually has like only 27,000 models, which is like 10 times smaller. So here, what we propose is that we propose a method that can learn the semantic parts only from the some language descriptions of the entire shapes. So what we do is that actually we collect the descriptors of each of shape from the some mechanical Turkers, and this is the way easier task for the Turkers than directly annotating over the 3D shapes. And also, even to make this process even easier, for the Turkers, we provide some references to the as kind of the shapes. So basically, these tractors are the references, and we are asking the Turkers to describe this target shape so that this target shape can be discriminated from the tractors. So what we exactly do is that we are having a speaker who describes the target shape, and then we are also having another person who is the listener who can identify the target shape from the destructors. So this is basically the setup, which is called the reference game, introduced in this paper, ShapeLab, published in the ICCB 2019. And the goal of this work, the ShapeLab, was to actually create a neural speaker and also neural listener, basically the neural net speaker and the neural net the listener that learn from this kind of the human speakers and the human listeners and imitate the process, basically describing the shape with the language and also understanding the language to identify the target shape. So the goal of this work is basically to make some neural network that can learn basically the connections between the natural language and the 3D shapes based on the data collected in this way, based on this kind of reference games. And in the architecture of the neural listener, basically the neural net takes a utterance, basically a language description, and the 3 other shapes. And one is the target shape, and the other are basically the structures. And the network basically classifies the target shapes using the architectures like this. So if I just briefly explain the high-level goal of this work is that basically if we have the kind of for example, the utterance of the leg here, then the neural listener here basically finds the lag from the shapes. So when the input shape looks like this, we are basically making the neural network so that it can first find the parts that we need to see, basically to identify this kind of target shapes. And then we actually, for this kind of the process of finding the parts, we are using a attention module that can basically highlight the regions that we need to see to make this kind of discrimination. And the neural listener is basically seeing this part and then finding the target shapes across among this kind of 3 shapes. So we are not only finding the target shapes among this kind of given shapes, but also we find like which part is described in the given the language descriptions. So we are basically discovering the semantic parts from the very weak supervisions, which are basically these kind of the language descriptions of the very holistic representations of the entire shapes. And this is the work which is actually not published yet, but under review now. So let me skip some details of this work because I'm running out of time, and let me just go into some results here that, so these are some results. So the left one is the input shape, which is actually pre-segmented using the method called the BSPNet. So BSPNet can, accurately somehow detect all the boundaries of the parts, but it's kind of like over-segmenting the input shapes. So it's over-segmenting the shape into the many small pieces, many small convex shapes. And on the right-hand side, these are basically results when the network is trained, even without any, the semantic, the segmentation as the supervisions. So these are the same case. There's some cases that our outputs actually are basically matching the ground truth, but here are also kind of some of the failure cases. In the ground truth, there is no armrest, but in our case, we are finding some of the armrest here. But actually, this might be even more kind of natural the outputs that we are having the armrest here. So this might be actually the case that even the ground truth may not be correct. And these are some other big examples. And also there are some kind of the failure cases that we are having some lag part here. But actually, it also makes sense that we are having some lags on the bottom of the chairs. So we are, and also for the other cases, we are also almost perfectly matching the ground truth without having any supervisions of the semantic segmentation. And also some interesting result is that while we train our network only with the chairs and the descriptions about the chairs, the network can be also generalized well to the other classes of the shapes. So this is the examples that we are finding some semantic parts of the tables when you train the network with the chairs and the descriptions of the chairs. And this is also another case that we are finding parts of the airplanes using the network, the same network trained with chairs. Okay, so let me skip some details. And so in this work, basically, we show that the language descriptions of the holistic some representations of shapes actually can be used to discover some of the semantic parts. And for that, I skip some details, but we made a kind of the careful design of the attention module so they can discover this kind of the part segments through learning the attentions in the case of the identifying the target shapes from the distractor shapes. Okay, so in summary, I introduced 3 different works that learned the composition structures from the 3D shapes. The first work was about the supervised learning and leveraging the full supervisions coming from the CAD models to fit the primitives to the 3D shapes. And the second one was about the unsupervised learning, basically finding the part structure by learning some plausible deformations of the 3D shapes. And the last one was about some weakly supervised learning, and we showed that the part segments can be actually discovered only from some language descriptions of the entire shape, but without having any kind of the semantic segmentation supervision. So here my takeaway messages is that I just wanted to give some my answers for these kind of the high level questions. So the first question about what sort of the supervisions can we use for learning this kind of the compositional structures? And I showed some examples using some full supervisions coming from the CAD models, and also using some language descriptions as kind of the weak supervision. And for these cases, I also explained some ideas about what would be kind of the best ways to leverage this kind of supervision. And for the first case, I also showed some examples combining some best features of the neural net, the predictions and also the optimization. And the second one was the case of using the attention module to learn from this kind of the weak supervision. And the last question is about how can we even guide the neural network to learn this kind of the composition structure even without the supervisions. And also I provide kind of the examples like decomposing shapes while learning the shape, the variations, the deformations, but there can be also multiple other ways of learning some the decompositions in a kind of the unsupervised way. Okay, so this is the end of my talk, and I will be happy to take some questions.
Thank you very much. Thank you, Minhyuk, for the great talk. So now we are in the Q&A session, and I think we don't have any questions from the audience yet. So let me start start with my question. So about the third method, about the language-based segmentation. So in my understanding, it can handle objects with a few parts, like 2 or 3 parts in my understanding. And I'm wondering whether it is possible for the network to handle objects with even more number of parts or finer grained parts.
Yeah, that's a great question. So actually, the reason why we just found some kind of the coarse grained parts is that actually, from the data that we use, basically we use the language data collected from the shape plot. But when you see the data, basically most of the utterances that we use, they do not have any kind of some descriptions for the small parts of the chairs. So people typically try to see kind of some big parts to basically see the difference between some kind of the chairs. So that was the main reason that we could not find some kind of small pieces of the parts using based on our method. But what we tried is that if we have some kind of the language descriptions for the small pieces of the object, then our method actually could find this kind of some small parts. So what we tried here is that since we did not have any kind of some language data, we also synthesized this kind of the language data by actually having this kind of some finer grained parts, which are annotated in the data set called the partnet. So we synthesized some kind of some language descriptions based on this kind of some kind of the part names that are used in this partnet. And when you use this kind of some synthetic language data describing some small pieces of the parts, actually we could find some kind of some small some parts like this. So we could actually we could find some of the some subparts of the kind of the components that we found. Like, so we could find some like kind of some small pieces of the leg or some kind of slats of the chairs, and also kind of some small pieces in the tables like this. So our method could actually find this kind of some fine-grained parts, but actually the limitation was that, actually we could not actually somehow guide the Turkers to make some kind of descriptions about these small pieces. So that will be also kind of the one of the future work in this work.
I see. Thank you. We have it's almost time, but I think we can accept one more question if the audience have. Probably no. Okay. So let me ask the last question. So quick question. So about the first method, about the fitting, primitive fitting. In my understanding, the method assumes a fixed set of primitives, like spheres or plane. So my question is how difficult it is to support like parametric surfaces, such as nerve surfaces or like that.
Yeah, that's also a really good question. So actually, I couldn't prepare a slide for that, but actually, our kind of the future work of that direction was to actually handle some more complicated kind of types of the primitives. Actually, there is another work which is it's kind of the follow-up of our work. I forgot the exact name, but actually there was kind of another follow-up the paper which was basically dealing with the nerve surfaces. Actually, and also along with this kind of the 4 types of primitives that we use in our work. And we also did another project, which is also handling some extrusion cylinders. So we are not just finding these cylinders, but actually we are basically making some of the primitives by having some 2D sketches and extruding this 2D sketch into the 3D space. So that was kind of the way more complicated types of the primitives. So we also basically extended the idea to handle this kind of some more complicated types of the primitives, but still there can be more. There can be some more types of some many complicated types of the primitives, and there will be still kind of the lots of things that we need to do along that direction.
I see. Thank you. Thank you very much. I think it's time to conclude this webinar. So, okay. So thank you, Minik, for the great talk. And thank you again to Wei Wei and Minik for the great talks. And also thanks everyone for attending this seminar and watching the live streaming. So yeah, this concludes the session. So thank you very much.
Thank you.
Thank you. Bye-bye.